Hello, everyone, and welcome to today's public webinar with TPC entitled Hydraulics, What You Need to Know to Troubleshoot. My name's Ryan Smith, and I am joined here by our instructor for TPC. His name's Ron McGarry, and he's going to walk us through all the details today about hydraulics and what we need to know to troubleshoot them. He has got years of experience in the field, and he's going to really be able to walk us through for the next hour here together. Before we get started, though, I would like to get us started on some housekeeping items about this webinar. The first thing I would love for everyone here to know is that this webinar is live and in the moment. So if any of you have any questions you would like to pose to our instructor today, feel free to use what we call the Q&A. If you look at the bottom of your toolbar, you will see a button that says Q&A. Use that to answer your questions, and we'll be able to provide answers at the end of the webinar. We won't pay as much attention to the chat, so try not to use the chat window and instead use the Q&A button. The second thing is that this webinar is being recorded, and the recording of this webinar will be made available on the TPC website about 2 to 3 business days after today's webinar is concluded. And with that, you'll also have the ability to download the PDF of these slides as well. And finally, since this is an informational session, there's no certificate or kind of thing that comes along with this. But if you are looking for an official certificate of completion for an official training, I do highly recommend you attend one of TPC's official 2-day hydraulics classes. Now, before I hand it over to Ron, I would like to start today's interactive session with a little poll, just set of 2 questions to learn a little bit more about who is here today. So what you are going to see is a set of 2 questions coming up on your screen right now. So you should see 2 questions, and you can go ahead and click your answer with your finger on your device or your mouse to click your answers and hit submit at the bottom. The first question is, how many years of experience would you say that you have working on hydraulic equipment? Do you have less than a year's worth of experience, 1 to 5 years, 5 to 10 years, or more than 10 years working on hydraulic equipment? We're getting some good answers coming in there. And question number 2 is, what type of hydraulic equipment do you presently work on? And you can select all that apply here. Do you work on industrial type of equipment like cranes and winches? Are you working on mechatronic equipment like robots and automation? Are you working on cylinder-based equipment like rams or presses? Or are you doing general maintenance like piping, checking for leaks, and that kind of thing? All right, good. We're getting some good answers coming in here from the audience. Give you just a few moments to provide your answers. All right, good. It looks like our answers have evened out. I'm going to go ahead and end that poll. Thank you for your responses. And I'm going to go ahead and turn these results back to you so you can see how we answered. So it looks like the winner here is that about 34% of you have less than 1 year of experience on hydraulic equipment. And isn't this great that we get to be here on a session where we learn a little bit more about it? So that's going to really help me and Ron as we get into this session today. And then the next of you, 30% of you, have between 1 and 5 years of experience. So you've been working on them a little bit, but maybe not, for the entirety of your career. But then there are some of you, 27% of you, that actually do have more than 10 years of experience. So the experience on today's session ranges across the map, which is really great. And number 2, what have we been working on? Looks like most of us, 74% of us, are doing some general maintenance of just the piping and checking for leaks in the hydraulic system. Whereas the next subset of us, 58% of us, are working on those hydraulic cylinder-based equipment like rams or presses or something like that. And so pretty much all across the board there as well in terms of what we're needing to work on. So what I'm going to do is stop sharing the poll. This window should disappear from your screen now, and make sure you have full screen as possible our presentation, which says hydraulics. And from there, we'll go ahead and hand it over to Ron. Ron, thank you so much for being here.
Good afternoon, everyone. We're going to be talking about hydraulics and what you need to know to troubleshoot. As everyone knows, to troubleshoot, we have to know a few things about our system. That's what I always say as an instructor is you have to know your hardware. So I've been in maintenance management and maintenance supervisor for a long period of time. And so if you know your hardware, if you know your system, then you're able to troubleshoot your entire system. So we'll be taking a look at what is all involved with our system. So we're going to take things apart virtually here, obviously, and then look at it segment by segment to see what each part of our hydraulic circuit, how does it function with our whole, the reservoirs, the directional control valves, and so forth. So we'll look at those. Troubleshooting is a big deal, as we all know. What is FluidPower? what are we trying to accomplish? We need to separate those out. Once you separate those out, then you're able to troubleshoot it. When not only just troubleshoot, but you can troubleshoot more easily, more efficient, quicker, which obviously, as we all know, makes the bosses happier, right? So FluidPower, that is the technology, as we all do know, that with the generation of control, right? Transmission of power using pressurizing fluids, can be said FluidPower is a muscle that moves industry, right? FluidPower is used to push, pull, regulate, drive virtually all the machines of modern industry, 100%. And would you believe it or not, we used to use water, right, as the hydraulic fluid. Now we can ask ourselves, how come we don't use water now? Well, obviously that answer would be contamination. Contamination is the #1 issue with our hydraulics. That's why filtration is critically important. And where do we put our filters? Do we put them straight from the tank, or are we looking at on the return side, and a return side going back to the tank, which is critically important as well. So the first hydraulic fluid was water. We don't use it anymore, all right, because of the contamination. There's other issues that's involved with water as well. So we'll take a look at those as we move through here. So what do you want the hydraulic system to do, right? And so that begins with there are two different types of fluid systems, fluid transport and the FluidPower. Fluid transport systems, that is, their sole objective is to deliver the delivery of fluid from one location to another to accomplish some useful purpose, right? So how am I going to deliver it? Now, we're not really going into design engineers or anything, but as maintenance technicians, as floor engineers, we really need to know what do we have for our hardware? What size motor do we need? What size pump do we need? And so forth to accomplish our task. What size reservoir do we need? Because if we got a certain size motor, a certain size pump, you definitely don't want to run out of hydraulic fluid throughout your whole system. That would not be a good thing because you can't run pumps dry, right? And so we look at our fluid transport systems. How am I going to accomplish my delivery of my fluid from point A to point B? My FluidPower systems, what are they? They're designed specifically for the work. We need to take a look at what are our loads in our hydraulic system. What I mean by loads is how heavy is it? How big is it? We really know the mass of that load. So we are going to talk about some formulas involved here that is directly related to our hydraulics. We're going to get to a little bit about the physics, because if you go into maintenance or have been in maintenance at all, there's a lot of physical work. Physics plays a huge part in our hydraulic systems, our electrical systems, our mechanical systems, electrical and so forth. So we need to know what those are. So we have the 5 basic hydraulic system components. And so we have our power input device, control devices. How are we going to control it? Are we using some sort of, I don't want to get too much into the weeds here, but are we getting to the PID loops? Do we want a complete feedback? Are we using 420 milliamps, 0 to 10, 0 to 5 volts, and so forth? Power output devices. What are those? Conductors. This is a huge a piece of the equation there. Are we using hoses? Are we using piping? What size piping? What size hose? What type of rubber are we actually going to use? The manufacturer of the rubber hose. That's a big deal. And then the liquid. And so is liquid going to stay cool or consistent throughout our hydraulic system as it travels throughout the piping or the conduit or the conductors that we're doing here? The fluid, as it travels, creates friction between whatever surface that we're working with. And so it could be that hose, that rubber hose, or it could be that metal pipe. Either or is creating that friction. So the smaller the conductor that we're actually using, the more heat's going to be generated. So how much heat can we withstand before we put in a heat exchanger? And so this is what we have here. This is the hydraulic system that we have. So we have a reservoir. And so these are just pictorials, right? And so how are we going to get from the reservoir to the hydraulic cylinder to our actuators that we're actually trying to work or function of? We have our load out here. And so at some point, our system will heat up. So we need a way of controlling that heat, again, with the friction. How many positions our directional control valves we're going to have? A control lever here. The accumulator. What if we lose pressure? And so if we lose a pressure, it is a shock to the system. So we need an accumulator to help keep that constant pressurized system throughout. So we need to have that. And then obviously we got to have our pressure relief valves or relief valves in the system. Big deal about safety. A power input device, right? What is that? So pumps provide power to a hydraulic system by pumping oil from a reservoir into the supply lines. Well, we need to take a look at, again, what size are pumps and motors and so forth. What are we actually trying to pump? What is the viscosity of the fluid? How thick is it or how thin is it? And so all these factors come into play when we're trying to work with our hydraulic system. Again, know your hardware. Once you know your hardware, then you're able to troubleshoot your system quickly. And then that way you get your system back up and running on the reliability way. Reliability maintenance is a big deal. All right, control devices, valves control direction, pressure and flow of pressurized oil in the actuator of the hydraulic system. So where do I want it to go at a certain point in time? So those are big deals. What is the amount of pressure that I need? Again, we need to look at some of these formulas: pressure, mass, acceleration, the force, what is required. So the flow of pressurized oil in the actuator to move that particular load. That's what we want to know. That's part of our control devices. Then we have our power output device. The power output device is where hydraulic power is converted into mechanical power. So that is our cylinders and motors. Again, we need to know these things. We need to know these items so we can know our hardware, know our system. Goes back to the qualified person. So once we get to know these things of our whole system there, again, we're able to troubleshoot it quickly and get everything back up and running again. Conductors or pipes and hoses need to transmit that liquid between hydraulic components. So we also need, when you look at the hoses or the piping, we have working pressures, we have bursting pressures. What types of hoses are we going to use? ISO, SAE type hose. And so these are things that we need to consider when we're looking at our hydraulic system. I've been through a lot of experience with some of these, and choosing the wrong conductor could be very, very dangerous. And we'll see some of these hydraulic injections, what has happened to some individuals that were actually in the hydraulic field, not choosing the right ones or being too close to the system when it did rupture. A liquid, so what is that liquid? A liquid is used as a medium to transmit the power, the oil in a reservoir. Okay, well, how much liquid, how much oil do we actually need? And so usually we need to find out, what is the flow rate? What is my gallons per minute of oil in my system? What you want to do, this is a small formula here that you can really write down or look at. So what we want is 3 times the flow rate is going to tell us the size of the reservoir. And so that way we're definitely going to know that we need this much oil so we don't run out of oil, right? Run out of hydraulic fluid in our system. Again, you don't want to run anything dry because this definitely wouldn't be a good thing or ruin our seals and our pumps and everything else. So you don't want to do that. Most of them, whenever I do these courses and teach these courses, the students want to know, what do the symbols mean? What are they? And so we put together this here a great pictorial. Over here, so we have a tank, right? And so this tank right here, but what about this tank? Well, this tank is not closed in, correct? And if it were closed in, it would be a non-ventilated tank, right? But for this guy here, this is a ventilated tank. It's non-pressurized because it's not closed in. And so as we move up the line here, we have some filters. Filters or fluid conditioners, if you will. Fluid conditioners are usually identified by a diamond, just like you see here. So these are types of filters that we need to have. Now, we have another filter here, right? And so then we have a hydraulic. And how do I know it's hydraulic? Because this guy here is colored in. So if it was not hydraulic, this would be not filled in, and it would be pneumatic. But for our purposes, this is our pump here, and it is colored in. So it means it is a pump. All right. So usually, as we shown here, so this is our pump, but this is our motor over here. It is critically important to know how our motor is really connected to our pump. And we have a direct coupling, a closed coupling with the motor to the pump, or we have other couplings that we can choose from. All depends on the application. I don't get too much into it, but we have our motor and our pump. Alignment is critical. Matter of fact, alignment is the /misalignment is the #1 failure in the United States in manufacturing. Okay, so if we don't have a proper alignment between our motor shaft and our pump shaft, guess what wears out? Our motors and pumps and the bearings. Bearings are critically important. And so if you don't have that proper alignment or the proper shimming of the motor and the pump, so you can have that proper alignment, bearings will fail very quickly. But as we see here, as we have our pump, we go into a pressure relief valve here. And so if you, once that pressure has been reached at a certain point, yes, we will have our fluid running back to the tank. So this is part of our return filter, right? And so this is the filter that's coming up, filtering the oil, critically important. Contamination, like I said before, is number one with hydraulics, let alone the misalignment part. And then we have a directional control valve, a DCV. So what type of direct control valve is this? So this is these are envelopes here, little boxes, right? And so we have 1, 2 position. So we can call this a 2 position, 4-way, right? So the fluid can go 4 different ways over here. And this here guy is a hand lever, and it's also got a spring on it, so spring return. And then over here we have an actuator of some sort, right? So this actuator can extend or retract. So that means it's double acting, all right? And this is the pictorial of this little actuator here. So being able to, this is the simple application, being able to identify, and I encourage all the students who take these classes, of course, to go out once they learn some of this information. So transfer it, if you will, to your real world application. Go out to your shop and write down, see what you actually have. What kind of tank do we have? What kind of pump? Write down the information from your pump data plate, from your motor nameplate as well. So we need to look at these things as we, in our own shop, become more familiar with it. That way you do get to know your hardware. You get to know your hardware, the different types of systems through there, then bam, you're able to troubleshoot it very quickly. Here we have the tank over here again. So a hydraulic pump motor unit. So when you see a line like this right here, that means it is an HPU unit, hydraulic power unit. And so everything is connected together, just like we saw on that last slide. And here is our mechanical coupling, or linkage between the motor and the pump. Okay, very, very important. Over here is a little pressure gauge. We can see what a pressure is coming through our lines and a pressure relief valve and so forth. And then we have another pressure gauge over here, external relief valve. So this just means, so you might see 2 or 3 tank symbols over here. I got 1 tank. That's all I really means. But everything is flowing back to the tank. That's what it's telling us. And then we have our directional control valve over here. So again, so this guy is more than 2, right? So we got 1 envelope, 2 envelopes, 3 envelopes. So that's 3 position, 4-way on this guy. And then we have our solenoid. So it's electrical. So in most cases, we have, the range from 12 volts DC to 24 volts AC on our activation of these solenoid valves. And then up here we have our pressure gauges on our cylinder. And so what type of, how much pressure we have on one side, on the other, that's perfectly fine. And then that's our actuator on this side. So over here we have our blind side of the cylinder and the rod side, or something called this the end cap, if you will, the cap end. And we'll see once we have the pressurize on this guy, it will extend. And once we get done extending or doing our work, whatever load that we're trying to push, then it will retract. Once it retracts, all the fluid will come back to the tank through the return line filter, and then we're done at that point. So making it work, very simple. As you do know, I went from the bottom up. And so that's how you read these hydraulic schematics, because you're reading from the bottom up versus electrical schematic. You're going to read from the top down, left to right. On these hydraulics, you read from the bottom up. This is where my motor and pump is, and pumping fluid all the way through. Critically important, right? Knowing how to read your hydraulic schematic and knowing some of the components in your system. Critically important. And so maintaining hydraulic systems requires calculation, so don't let that scare you. There are some, obviously we have apps for all that nowadays, right? Physics involves just about every aspect of our lives. It is about physics. So there's a lot of physical aspects with hydraulics, electrical, and or mechanical there. Especially comes with forces when they're acting within a hydraulic system or any other fluid power system, such as pneumatics. So we're talking about fluid power systems. Pneumatics is a fluid power system. So we need to look at these things as we move along. Calculating horsepower. So once you, again, use your apps on your phone, I'm a firm believer in Bluetooth technology and using your apps, but you really need to know where these numbers come from too, right? We have constants that we use in hydraulics, 2.31, 231, 746 of horsepower. We need to look at all these things. So our horsepower over here, how do I get my horsepower? You need to know what my distance is. What is my stroke length of my actuators? My force in pounds. How much time do we have? All these things are huge. When you see a Q, right? Q always refers, in hydraulics, Q always refers to my flow rate in gallons per minute or liters per minute, wherever we have. So we have a flow rate. How much flow of fluid can we get at a certain time? And then our P is for our pressure in pounds per square inch and so forth. So these are the formulas that we currently that we use throughout with our hydraulic system. So it's a big deal. Mechanical. So we have these constant values, 746, 63025. We need to know what application we use for these formulas. So they're different they may be different in each one. All depends what the application is. Know your hardware, know your whole application. Go out to the shop and see what is going on out there, right? So Pascal's Law, as I said before, it should be no surprise, is that, yes, this is about physics, right? You need to know a little bit about physics. And so pressure is transmitted undiminished. That's very important. Undiminished and confined body of fluid and acts at right angles to all surfaces contain fluid. Well, what does that mean? That means if I got fluid in the system, I'm going to push down into a container. It doesn't make it where that container is contoured or a cylinder. It's going to push that pressure throughout that container. That's exactly what that means. And so Blaise Pascal is a fundamental law of physics, there we go, which is the basis of the fluid power operation. And here's a form that we need to be very familiar with. So pressure equals force divided by area. And a closed container containing a fluid at rest, increased pressure at a point will cause increase in equal amount of pressure at all points throughout the fluid. Also, as we get to know about some of these other formulas that we're using, when you put fluid in a cylinder, right, and you put pressure on it, what's going to also be created is the heat. So we need to look at the heat. When you're dealing with the hydraulics and so forth, and the packing, we're trying to repack the cylinders, you need to really know what type of packing, what type of seals I'm going to have, or what are the temperature readings are of each seal, and or the types of seals in there. So this is where you get to know, we're not material science engineers, but we need to know what the type of rubber and what are the temperature limitations to those rubber seals are. If you don't, you put something in there, let's just say, for example, rated 120 degrees Fahrenheit, you're going way above that. And so it's going to disrupt that seal. You have a leakage and your system will not work properly. So we need to look at these things before we put everything together, just like here. So we need to know what the pressures are. So this area is different and this area is a little bit bigger, right? And so a small area can create a big difference in lifting our force, our load, what we're trying to move. All right. So here we go with our force equals pressure times the area. I usually put into a little pie chart like this. If you just put your finger over the P, and so or the A over here, wherever the case may be, we need to know where the volume is, or distance, movement in inches. And so this here line means this is going to multiply, this be divide. So force equals P times A. And then if we're trying to find the area, force divided by P, and we're going to find that what the area is. So it can be changed around. So I put it like this instead of using algebraic manipulation throughout the whole system. I can just do it like this. So very easy to do. And volume equals area times my distance over here. So how far can we go within our hydraulic system? Basic formulas, nothing real rocket science. We can handle it. And a little bit of example here. So we have our force moving through a cylinder with our piston here. We have a square inches, right? So half square inch. So if you do the math on this guy, pressure times the area, force equals pressure times the area, right? So we got 10 PSI moving throughout the system through our gauges. And then we can move that 50-pound force, okay? So there are some other things we need to take a look at when we're dealing with our systems, the piping, the conduit, the fluid, how far the viscosity of the fluid. And we're talking about viscosity index, which has to do with the temperature, right? So in a nutshell, with the force here, so force equals pressure times the area. Our PSI, what is our pressure? Our area. We want to get the force amount that we can actually move. Terminology is critically important, so know your terms when you're talking about fluid power. So the fluid power industry does continue to grow. The types of number of equipment and the feature also grows. A standard of terminology can be evident. All this can be found in FPA.com, National Fluid Power Association.com, all the way through here. Again, it's critically important to know your hardware, right? So 2-position valves, 3-position valves, etc. So when I put my system over here, let's just choose this one here real quick. Completely block center. So we got 1, 2, 3 position, 4-way. Once I put my actuator in the center position, nothing's moving. So we call this the neutral position, right? You have to be careful when you put your system in the neutral position. That does not necessarily mean that fluid is not flowing. Fluid is flowing, but it's not stopping at that point. So what you got to worry about is what type of pump am I going to have? So if you put that in a neutral position, my pump is always running. That means I'm creating a lot of pressure within my system. So it had to have some way of relieving that pressure. And it's going to go back to the tank. All right. So we need to have some other lines when we go to look at our system, some other our conductors, our hoses or pipes, relieving that pressure back to the tank. So that's critically important when you're working with 3-position, 4-way directional control valves in this regard. Now, obviously, you do see these here going back to the tank over here. That's going to determine what size pump, what size motor, what type of pump, what type of motor I'm going to have for my hydraulic system. These guys over here, this is 2-position for smaller applications that we do work with. And again, this is our basic hydraulic system here. Reservoirs are huge. Knowing what your reservoir is made up of, you have baffles inside of reservoirs. We have our hydraulic fluid in there, right? But is our hydraulic fluid clean or dirty? So we need to look at the filtration. Filtration is huge. Like I said before at the beginning of the seminar, if we don't have proper filtration, then we're running this contamination all the way through our system, decreasing the life of our components, our valves, our pumps, and so forth. And so then you're going to get a blockage somewhere in the line, and then creating a lot of pressure somewhere. We're not going to get our flow rate. We're not going to be able to do the work that we need to do. So contamination is huge. We need a proper way of filtering our hydraulic fluid. And believe this or not, so when you get a new 55-gallon drum of oil, it is not clean. It has to be filtered. And so you can see these little portable filtration units that look like they're on a dolly, filters. That's the way to do it. So when you got some new fluid coming into the shop, if you're going to put new fluid in, obviously you want to drain or get rid of the old fluid. You want cross contamination, because if you do, you're putting that contamination back in your system again. It's not going to do you any good. Then you have your pump, your pressure relief valves. As I said before, your pump is creating flow, and your piping and so forth is going to create that pressure, establish pressure, develop pressure throughout our system. And so we need to have that. If it becomes over pressurized, and you have some way to relieve that. Our control valve, this could be our 2-way or 3-way or 3-way, that's fine. And then a 2-position or 3-position direct control valve as well. Are we going to extend, or are we going to retract? When we retract our piston this way, we do have fluid going back to the tank. So usually that's less than 100 psi, as low as 60 psi. But on the return side, we definitely got to have a filtration unit. So the purpose of the reservoirs, so serve as a heat sink. Sure, absolutely. In here, so this is what we do call a strainer. A lot of people want to call this a filter, but it's really a strainer, right? It's really a strainer. Using the proper terminology is key, because when you do talk to your engineers and so forth, as a maintenance technician, prefer to obviously to use that proper terminology. Then we have our system return line with fluid flowing through here. A breather, critically important. If our reservoir is not properly breathing, then it could heat up on the inside. If we have other contaminants, our environment getting into our fluid, that's not a good thing. A lot of manufacturers put desiccants of some sort on top of our reservoirs to keep them nice and clean. The air going into the system nice and clean. Our pump inlet line over here. So we have the suction, then we have the discharge throughout our system over here. Provide for secondary cooling system. Provide for addition for fluid. Indicate fluid level. The reservoirs are critically important. On this side over here, we have sight glass gauges. Make sure those are always clean. I've been into a lot of plants where the site glass gauge is not clean at all. So how you know what your fluid looks like or how much fluid you have in there? So keep your system nice and clean the reliability way. Just real quick over here, positive suction head for a pump. So we have NPSH, net positive suction head. And so we need to look at some of those terms and terminologies. Knowing your hardware, knowing what they can do is critically important to establish good troubleshooting skills. So loading of hydraulic system changes the different flow rates needed. So throughout our system is, again, critically important. Low flow pump supplies pressure, and the high flow pump supplies that flow. So we're maintaining, right? When you use two pumps like this, we're maintaining our system pressure throughout. And so you'll see this in a lot of complex applications. And we have a spring-loaded check valve all the way through here to pilot relief valve for this guy. And everything here is going back to the tank. Restrictor to dampen response times, reduce shocks in the system. Anytime you have fluid flow through a piping system or a hose, you're going to have some sort of shock, and you want to dampen that shock. So there are shiv dampeners that we can have in our system to relieve. If you have a lot of vibration in your hydraulic system, what's going to come loose? Your couplers, your fittings, and everything else, and then you're going to have leaks. So leaks cost a lot of money. You don't want that to happen. ISO, International Standard Organization, and your ANSI, American National Standards Institute, and so forth. So NFPA, National FluidPower Association. So we show most of our symbols in ISO. There are some graphics. It's also critically important to know what you're looking at. So what we're showing here is like, are we showing a graphic symbol or are we showing an ISO symbol? Most of the time with hydraulics, it is ISO and not our graphics. What we just saw were ISO drawings. Pilot lines, being able to identify what these are. Our drain lines, so you see the difference in the dash marks here, a little bit shorter, smaller for our drain lines. Flexible line, like our hoses. When you're talking about our hoses, when the flexibility, can you bend the hose too much? Absolutely. So if you bend the hose or you go beyond the bending radius, then that hose now has a kink in it, and it's going to restrict my flow rate. And so I need to look at those things. You don't want to do that. Make sure you get the right size hose. And lots of times, in a lot of manufacturers, like I did for whenever I was running a maintenance crew, I'm going to make my own hose, right? So I'm going to buy hose and buy my fittings. I got a crimper. I'm going to put my crimp. I'm going to cut my hose to the right length. I'm going to put a crimp on my hose and then put it on the machines itself. So that's a hose program. I encourage everyone to do that. So that includes another skill set for the maintenance technician. So now they can make their own hose, relieves the lead time of getting new hose in. Plus, if you have somebody else making your hose, as we all know, it's very expensive. So we have lines connected here. So we have an intersection here, and then we have lines not connected. So a little bit of a camel hump here is what we're talking about, a little bit of camel hump. So they're not connected, they are here. So being able to identify what lines we have in our system is important as well. We already hit on this already. So when they're filled in, right, it's hydraulic. When they're not filled in, it's more air or pneumatic, right? Let's look at this, pointing out, pump or compressor. So it's pointing out, so that is my pump, right? It is my pump or my compressor. Now, the thing to help you remember that is that my pump is pumping. I'm going to put something out there. And so that is the direction of pump output flow. On our motor, so motor is always sometimes, right, in our system, it all depends upon the application, it is turning, right? So we say the motor side, the hydraulic motor or the air motor, when the air is pointing down, that is the motor. Obviously, the pump, we're going, that is the output. And so it's going in that direction, in the output direction. And then with the motor is pointing down in the input direction, if you will. So there are still outputs, but we still have the direction of the triangles here. So the hydraulic pump out, the hydraulic motor, the motors are always in toward the circle. Again, with my hydraulic power unit, you saw a symbol on that fairly quickly. So everything is together. And then we have our motor to pump. The thing about your hydraulic power unit, again, is make sure it's clean, clean, clean. And so usually it all depends on how big it is, right? So you can put a PM on this to change your hydraulic fluid. But You just don't want to go over there and change it because the PM said so. So you can do an oil analysis. That's more of your predictive maintenance technologies. And so you don't want to do an oil analysis. The oil analysis is going to let you know, right, what is failing upstream of your system, because whatever is in your system upstream from the reservoir, it's all kind of going to come back to my reservoir, to my tank. And so if you do that oil analysis, you'll see what is made up of, tin, aluminum, etc. And that way you'll be able to identify, well, this component upstream is failing, so I need to be more proactive and take care of that. Keeping your reservoirs clean is critical all the way through. So we've got a motor and a pump, or our main hose. There's baffles on the inside of here as well. So these are some of the things that really need to take a look at. What type of pump? So all depends upon our application. So we have some internal and external gear pumps throughout our system. So hydraulic systems require pumps, and their systems require compressors to provide input energy to the actuators. Understanding pumps and prep give you a better knowledge of overall operation of your entire system. And so there's positive and variable displacement type pumps. What pumps are there to choose from? A lot. And so just remember, our pumps do not make pressure. They create or establish that flow. We need flow. So whatever our piping system is, our hose, or let's just say, for example, black iron pipe and so forth, going out to the discharge. And so that is what really creates our pressure there. Our pump is pumping. So when I discuss pumps making pressure, it always assumes we have sufficient resistance, right? Now we're talking about the viscosity of the fluid within our system. Resistance to flow allows pressure to build in the system, right? As pressure builds, flow tends to slow, it will. And so when the purpose of our pressure relief valves too there, right? When the restriction is removed or decreased, flow tends to increase. So as a consequence, the flow and pressure must be maintained, more horsepower must be applied. That's why we need to look at our system before anything else. What size motor, what size pump do we need? How much horsepower is required for our hydraulic system? Once you do know those things, again, you're able to troubleshoot a little bit better. Hydraulic systems require pumps and air systems to require compressors to provide input energy to the actuators. Understanding your pumps, again, is critically important for the whole application here. So pumps come in various types and styles. Of course, we have our centrifugal type pumps, as I mentioned already earlier, with our the internal and external type of pumps that we have. Resistance is usually just the weight of the fluid or resistance in the pipe, right? So we have these things. So this is external gear pump here. And so we have the suction of the fluid coming into one side and discharging out on the other side. So this is more of our positive displacement type pumps. This is commonly used. This is the external gear pump that we have. And so knowing what your pumps are for, how much pressure or how much can we put out, what is our rate, our flow rate, our gallons per minute through our system is critically important. Rotary gear pumps. So we have internal, and then we also, on the last slide, you saw the external. And so how the pumps operate, again, is critically important to your system. A qualified person, we really got to know your hardware. Again, that way you're able to troubleshoot it quickly and get your machine back up and running, get your system back up and running. In an outlet, so as the flow is coming through here, this guy is turning, and then boom, our discharge of the fluid out on the other end. On the power unit startup, and so this happens quite a bit. There's still pressure on the hydraulic power unit itself, and so we want to fill the pump with filtered fluid, right, to reduce or eliminate that contamination. The fill pump casing, ensure lowest pressure setting, because if you have a high pressure setting, you turn that motor and the pump, now you already have pressure on there. You're going to stall out your motor. And so that's what you don't want to happen. You can actually ruin your motor and pump also as well. Start and stop system while venting, adjust the output pressure system requirements, and then all the way through here. So check for your leaks and make sure you don't have any leaks in your system. So if you have something leaking out of your hydraulic system, you have contamination going in that same hole, 100%. So you don't want that to happen. Again, fill a pump with filtered fluid and all the way through here. Run the pump unloaded. So without a load, observe reservoir temperature at all times. Cleaning a hydraulic system, critically important. And so to drain the entire system to the reservoir, drain your reservoir and use offline filtration. So it's not in line with everything else, it's offline filtration. Replace your filters, that's a big deal. And then what I did in maintenance and so forth and do with maintenance is that we put the tag on there and who replaced it, and then when did you actually replace it. And so this gives you a clear indication. Of course, you have work orders as well, but you can use some sort of documentation for replacing your filters. Clean pump suction strainers, very important. Clean your reservoir, make sure it's all dry, nice and clean. Then on the outside, of course, you can make it look good and paint it and make sure everything is up to par. Professional and workmanlike manner. Close reservoir and refill, replace air breather, restart the system, take a fluid sample. Consider adding more filters if you really need it, right? Follow suggestions to make cleanliness levels. On your filters, it is important to know what filter I'm actually using, a 5 micron or 10 micron. I'm using a surface type filter or a depth type filter. I'm getting nominal filtration, or we're getting more absolute filtration. These are terms used in the hydraulic world as we move forward. So what about valve maintenance? I talked about heat. And so if your hydraulic fluid is overheating in the system, they will have an accumulation of fine particles in that valve. That's what we call silting. Valves operate erratically, partially, or even stop. They don't work at all. So and most of the time, we have these solenoids on the solenoid caps. So they energize it, but maybe they won't energize. You have to go up there and manually do it on these directional control valves. That means because something is stuck on the inside, the varnish begins to happen on the inside of these directional control valves. Now we have here hard coating from the breakdown of the fluid. Once your fluid breaks down, once the viscosity starts to break down because of overheat, your temperature is too high, then you're going to have what's called varnishing. So increased diameters, reduced clearances, and your valve is not going to be working properly. So those are important aspects to look. So FluidPower deals with transmission and control of energy by pressurized. So we go through here and we look at these things, and by pressurized fluid, absolutely. FluidPower deals with transmission and control of energy. Pressure is equal to the force divided by, remember the formula we talked about, is by the area. So pressure is equal to the force divided by the area. A spool of a direct control valve is shifted to different positions by the what we call the operator. Could be the hand lever, could be a detent, could be a solenoid valve or solenoid cap electrically with our system. And what about our actuators itself? What about the cylinders? So we definitely need to maintain those. We need to repack them if they leak. We have to make sure that no contamination gets inside of here. And so we have to look at our rod, our packing, what type of packing. Remember I said before about what type of rubber, what type of seals that we have, what temperatures are we working with, actually the fluid itself. And so there's been a lot of cases in past history where the fluid, the hydraulic fluid, is not compatible with the seals that are in the actuator, that are in the cylinder. And then what do you have? You have leaks. The seals will deteriorate in a short period of time. The reliability of the seals has now decreased quite a bit. And then now we're replacing these packing. And then your boss will say, hey, you just got done doing that a while back. So how come they're still leaking? Well, we didn't look at the compatibility between the hydraulic fluid and the seals we're actually using. So these are critically important aspects of it. My cushion adjustment. So if my actuator is flying out there really, really hard, I can adjust those with a little needle right here, cushion adjustment with a needle. So you can adjust that very easily at some point. Rod seals or rod wiper, very important. So if once your actuator is extending and retracting, and so if you don't have that rod wiper, guess what's going into your system over here? So you could have some small particles of contamination. The smallest particle of contamination can do the biggest damage, okay? Because they're small enough to go in there and cause gouging, deteriorate your seals, and so forth. So we have oil leaks pose a safety hazard, 100%. So if we have some oil leaking on the floor, somebody's walking by, they're going to slip and fall. So that's another issue. So we need to make sure that hydraulic fluid does not leak on the floor or anywhere else, because it does cost money. And then the efficiency of our system has greatly decreased. So efficiency of the system, we have a huge hydraulic system. We want to be as efficient as possible. We want to push this load or pull this load, whatever we're doing. We want to make sure we do it in a professional manner where the hydraulic fluid does not leak. So look at your entire system. Some people think that, well, it's hydraulic, it's supposed to leak. No. So with the current fittings, the technology that's behind the fittings that we have in the 21st century, there shouldn't be any hydraulic leaks out there. So we need to put more effort toward that and take a second look at our hydraulic leaks that we have in our system. So would you think of letting your car go for 100,000 miles? No. So we're going to be changing and looking at our fluid. Maintenance reduces troubleshooting 100%. So proactive maintenance, you got to be proactive in your hydraulic system. So look ahead, look at your predictive maintenance technologies that you're actually using. So we need to look at, see what we can do for our filters and filtration and so forth. Proper maintenance is one of the most important yet most overlooked requirement of a hydraulic system, 100%. So we need to look at our pressure, our loads, our voltages for our solenoids. What are we using? Again, get to know your hardware within your hydraulic system or whatever you're working on. Critically important. Without maintenance, costly downtime occurs. That's our reactive maintenance. Many troubleshooting hours and dollars are spent, right? So we can't have that. As of maintenance, a common thread that ties failures of hydraulic system is the contamination. Proper filtration is critical. So what causes the wear? Particulate or the contamination itself. If there were absolutely no particulate, there'd be no abrasive wear. So it's important that if a bearing does fail, you need to look at why did it fail. Take your bearing apart, look at the bearing to see why it failed in the first place. We can have spalling effects, we can have overloading effects on the bearing. Take a look at your bearing. Bearings tell the story of why it failed. The electrical fluting, possibly I don't have with your motor. Possibly that we're not properly grounded and bonded within our system. So we have electrical fluting within our bearings, which will cause marks, and then your bearing is not going to turn as easily. So if your bearing's not turning as easily in your motor or your pump, what does that cause? So we're talking about rotation, then we need to talk about torque. If I'm putting too much torque within my system because my bearings are failing, I'm going to require more amps for my circuits. And so now, if I'm requiring more amps, I've only got a 20 amp breaker, boom, I'm going to start tripping out my my breakers and so forth. So everything needs to work in conjunction with each other. So these are important aspects within our whole hydraulic system. So all the way through here, the tank, the stock price, and so forth, our bearings tell a story. And then our contamination with our centrifugal type pumps or whatever pumps that we're actually using, they'll deteriorate our impellers, our gears, and so forth. Filtration is critically important. So I talked about earlier with the hydraulic injections. So if we get a spike in our system, a large hit of our system, we have a leak. And so hydraulic injection, so we will start working on our system while it's pressurized as well. So that's not a good thing. We need to make sure all the forces are out of the system before we actually start to work on it. If not, things like this happen. And so this is a hydraulic injection. You can see where the input point, where the impact here, if you will, through this hand, and then it will swell your hand up. A lot of cases, quite a few cases, fatality is the end, right? And so, but the loss of the arm or a leg is critically important. And so not to do. So have some hydraulic injections up through here with our hands. Most of the hands, because we're trying to work on something, right? And take this valve off and take this fitting apart. We did not depressurize the system, and then you have that hydraulic injection going into your hands. So that's mostly occurs. That's why you see a lot of hand accidents in relative to the hydraulic injection instead of your feet and legs. To do a what we call a 5-minute checklist, if you will. So safety glasses, of course, personally locked out and tagged out the electric motor circuit. So that we have to go by the 70E regulations, which another course at TPC does offer. And so 70 lockout, tag out, Article 120. Personally locked and tag out the directional control valve circuit. So depressurize the system, verify the hydraulic pressure, 0 if we're going to work on it, right? And then install mechanical locks or blocks where necessary. Absolutely critically important for your safety and everyone else's safety. So when you're working on these systems with mechanical, hydraulic, electrical, make sure there's no forces on there. Troubleshooting power units, my dirty oil, components not properly cleaned after servicing. That is a big deal. So it happens a lot. Air breather left off. So some of the things that we can prevent, professional workman like me and every must do that. Pipelines left open during servicing. So what I did, I covered up with plastic, make sure it's all nice and clean, or caps, so nothing crawls in there and gets into my system. And I put it back together. Filter elements dirty but not replaced often enough. So these are critical things. All right, so this here brings us up to this point here. If you'd like to learn more about hydraulic systems, TPC can obviously help. At this point, let me see here. At this point, I'm going to bring it back to Ryan there, and then we can go from there. Does anybody have any questions or go through the system as Ryan did say, and then we'll go from there. Sound good?
Absolutely. Thank you so much, Ron. I really appreciate you sharing your expertise with everyone here. I know those of you who are tuning in from all around the country and maybe even all around the world might have questions about these hydraulic systems. Now is your chance to ask those questions. Again, go to the Q&A button on your toolbar, either at the top or the bottom of your screen, and type in a question for Ron, and we'll be able to get those answered in the next few minutes here that we have left to answer those questions. As you all are putting in those questions here and we're getting those in, I'd want to let everyone know about something interesting in terms of an opportunity for future learning after this webinar. There is a technical, what we call electrical troubleshooting conference. So I know Ron was talking about the lockout tagout and NFPA 70E. And if you're looking for a quick little bit of inexpensive learning, feel free to join us on our one-day conference where there's actually 2 full 8-hour tracks available to you on Wednesday, November 17th from 8 in the morning till 4:30 in the afternoon, Central US time. We're going to be talking about electrical safety. We're going to be talking about how to understand troubleshooting of relays and how to read different settings on a multimeter, all the way over to how to look at a full-scale ladder diagram and electrical schematics and all that kind of fun stuff. So if you're looking to learn more about electrical on top of hydraulics, let's continue talking and attend that conference. So that's actually coming up again in about 2.5 weeks from now, November 17th. And we're going to send you more information about that as the follow-up email to this webinar if you want to learn more. So we're getting some great questions starting to flow in, Ron, and let's see if we can pose a couple of those. So would you like to speak briefly about the idea of an accumulator? What does an accumulator do, and what are some do's and don'ts, let's say, about an accumulator?
Well, yes, we definitely need accumulators in our hydraulic or even pneumatic systems. Some of the don'ts, right, is to work on a system while the accumulator is still pressurized. So there should be a cutoff valve in there somewhere, or there is, to stop, or so you don't have any pressurized system downstream from the accumulator. Accumulators play a vital role in our pneumatic and or our hydraulic systems. And that vital role is to provide, number one, is to provide that system pressure throughout the system. Like I mentioned earlier about a leak in the system. So if the leak is there, with a small leak, could be a small leak or a large leak, the accumulator will compensate for that, maintaining that system pressure within our hydraulic system. And if you don't have that accumulator there, then you're going to lose system pressure, you're going to lose flow rate, etc. So servicing accumulators is very, very important, but you got to be really the qualified person. I want to talk about that. The qualified person work on accumulators. That means that really that special person. Accumulators, nothing to fool around with. They do have a lot of pressure on the inside of them, and so there's bladders. There's some of them have bladders, some are gas filled, or some have a spring or a tension on the inside of those accumulators. And so it's very important to relieve all pressure within that accumulator. If you do not, and if you open up a certain valve, you can have like 3,000, 10,000 psi coming at you, pounds per square inch, and that will penetrate your skin, or just like we saw there with the hydraulic injection. So it's critically important to know your hardware about your accumulators. Again, the purpose of the accumulators is to help maintain that system pressure throughout. Also, just real quick on the accumulators, the valves are open toward the accumulators and so forth. And so what about that initial shock? And so if you have many cylinders and pumps and working within your complex system, your accumulators will help soften the vibration, soften the shock throughout your whole hydraulic system. Thereby, but why that is important is because of this. And so if you have these fittings or these elbows, these 90-degree fittings within your system, elbows are just fittings, connections, and so forth, and a sharp 90 degree, or 90 degrees, 90 degree. But if you have a 90-degree elbow, and then all of a sudden you got an actuator hitting really hard within your system, it's going to, the accumulator will help absorb some of that shock and help again maintain that system pressure. So
Gotcha.
accumulators are very, very important to look at.
Absolutely. And thank you all for your curiosities and questions. I think we can take maybe one more question in the time we have.
Okay.
This is a good, pretty fundamental one I think we have coming in. When we have one of the hydraulic valves, let's say a solenoid operated valve or otherwise, what's a good method of troubleshooting a valve that won't open or close? What's a good way to kind of narrow down what might be causing that?
So again, what I've done in the past with these directional control valves that won't move, there is it's not really a push button, but you can push in on this. The small part of it's on the side or on the aft end of the directional control valve. Push in on that with your blunt end of a punch of your mechanical tool, right? Not really a screwdriver because it's rubber sealed. And then see if you can move the actuator manually. So if you can move it manually and not automatically through your solenoids, that means your inside of your direct control valve is working. But what really activates that valve? What actuates it? So with hydraulically it's actuate, electrically it's activate. So maybe on your solenoids, I need to check my proper voltage. Maybe make sure I got 24 volts DC or 12 volts coming through there with your meter, with your category 3 meter, by the way, category 3 or 4. So you can check your voltage, see if my solenoids are actually being energized to move it. If I can move it manually, then maybe, and I can't move it automatically through the electrical side, maybe it's something with my electrical. So if it doesn't move electrical or mechanically, then it's got something to do on the inside of that valve. So maybe the varnish has built up on the inside, could be a bent spool on the inside because of the contamination and so forth. Something got in there, and then now I got a bent spool, misalignment of my spool, or I was there. You can also have too much pressure within that directional control valve, also bend your spool over time. So those are some things you can take a look at, and then just take it from there. But I would see if I can't do it manually by the push button on the side, if you will, and then if it does move, then that's good. I'll check my voltage to my solenoid. If it doesn't, if my position doesn't move at that point, then it's got to be on the internal of that directional control valve.
Absolutely. Again, this is a deep topic that we can only cover so much in 1 hour, y'all. So I really hope that everyone tuning in, if you're continuing to want to learn more about hydraulic systems, we highly recommend you continue learning about hydraulic systems by taking an official 2-day course or an online course, or maybe sit in the classroom with Ron and really pick his brain about some of these things. Some of you are posing some specific applications you're dealing with and some selection of components you're dealing with. We definitely want to really encourage you to continue learning by calling that number, getting the conversation started. We can get you connected to future learning. For those of you asking about certifications and what it takes to be certified to be a hydraulic technician, definitely do give us a call. Certification means different things to different employers, but TPC maintains a big database and we can help walk you through that process. So feel free to call this number you see here to learn more. And in that note, I really thank you all for being here. Thank you for your time and your curiosity, and I hope you all have a great day.